In the modern era of computing, artificial intelligence has transformed from a theoretical concept into a world-changing reality. But behind every large language model like GPT-4 or image generator like Midjourney, there is a physical hero, the AI chip. Unlike traditional processors, these chips are designed for one specific, massive task, performing billions of mathematical operations simultaneously. Today, we explore how these silicon marvels handle the immense parallel processing required for neural networks. To understand AI chips, we first must understand the math of neural networks. At its core, deep learning is almost entirely composed of matrix multiplications. When an AI processes an image or a word, it represents that data as a tensor, a multi-dimensional array of numbers. To pass data through a single layer of a neural network, the chip must multiply a weights matrix by an input vector. This involves millions of multiply-accumulate operations, or MACs. In a standard CPU, these would be processed mostly one by one, creating a massive bottleneck. The fundamental difference lies in architecture, CPU versus GPU. A CPU, like an Intel Core i9, is a general-purpose master, optimized for low latency. It has a few powerful cores designed to handle complex logic and branching. However, a GPU, pioneered by NVIDIA, is built for high throughput. Instead of a few complex cores, it contains thousands of simpler cores. This is the SIMT model, single instruction, multiple threads. While a CPU handles tasks like a high-speed Ferrari delivering one package at a time, a GPU is like a massive freight train delivering thousands of packages at once, albeit at a slower individual speed. But the evolution didn't stop at GPUs. Enter the NPU and the TPU, or Tensor Processing Unit, designed by Google. These chips use a revolutionary architecture called a systolic array. Imagine a heart pumping blood through the body. In a systolic array, data flows through a grid of processing elements. Each element performs a calculation and passes the result to its neighbor without needing to write back to main memory. This drastically reduces the von Neumann bottleneck, the slow process of moving data between the processor and the RAM, which is the primary energy consumer in AI tasks. The biggest enemy of speed in AI isn't the calculation itself, but the memory wall. AI models are now so large with billions of parameters that they cannot fit into standard cache. This is why chips like the NVIDIA H100 use HBM, or high bandwidth memory. HBM stacks DRAM chips vertically like a skyscraper and connects them directly to the processor using an interposer. This allows for over 3 terabytes per second of bandwidth, ensuring that the thousands of hungry cores are never starving for data. Another trick in the AI chip sleeve is reduced precision. Traditional scientific computing uses 64 or 32-bit floating point numbers for extreme accuracy. But neural networks are surprisingly resilient to noise. By using 16-bit or FP16, 8-bit or INT8, or even 4-bit formats, chips can double or quadruple their processing speed and reduce power consumption. This process, called quantization, allows more data to be packed into the same memory space and processed in the same clock cycle, providing the brute force necessary for real-time AI response. Finally, as models grow to trillions of parameters, no single chip is enough. Parallel processing now happens at the cluster level. Technologies like NVIDIA's NVLink or AMD's Infinity Fabric allow multiple chips to behave as one giant superprocessor. These interconnects provide speeds hundreds of times faster than standard PCI cables. When we combine thousands of these chips in massive data centers, we create the computational power capable of training the next generation of artificial intelligence. From the microscopic flow of data in a systolic array to the massive scale of GPU clusters, parallel processing is the heartbeat of the AI revolution.